Let's start off by trying to take the derivative of this function right here in terms of our variable x. So essentially what we're looking for is we're looking for dy by dx, the derivative of y in terms of x. What's different about this question than previous questions we've done? Well, the difference is that it is not in terms of y. It's not explicitly isolated for y. So maybe our first strategy might be to isolate y. So to do that, I'm just going to do a quick rearranging. Negative 5y equals 3 minus 2x. Then let's isolate that y by dividing everything by negative 5. So y equals 3 over negative 5. And then minus 2 over negative 5, I'm just going to change that to plus 2 over 5x, essentially is what we're going to get. Now can we take the derivative? Yeah, that's pretty easy. That's just a linear function, right, with a slope of 2/5. So when we take our derivative, y prime, we know that first term is going to go away because it's just a constant, and the second derivative of the second term is just going to be 2/5, right, because the x is to the power of 1. So there's our derivative. So when we need to take the derivative of something like this, that's the first thing we could try. We could try isolating y and then taking the derivative. But what if we get a question that looks like this? So first of all, you might realize that we actually can isolate for y here as well, right? If I bring that negative 5 to the other side, divide by 6. So the whole thing's going to look like this. I'll just do it in one step. X squared minus 2x, if that negative 5 comes to the other side, it's going to be plus 10 all over 6. And that's going to be y squared, right, if we isolate for that. And then to isolate for y, to further isolate for y, we can take the square root of both sides, right? So y is equal to the square root of x squared minus 2x plus 10 over 6. And when we take the square root of both sides, we should always consider that there's going to be a positive root and a negative root, right? So we actually have to take the derivative of both solutions, the positive side and the negative side. We know how to take the derivative of this. You can use the chain rule to take the derivative of the inside and the outside and do it that way. So what I want you to do is I want you to try that now. Pause the video, try that now, and see what you get for the positive root and the negative root. So here we go. This is the derivative that I got. Basically what I did is I first took out the over 6 as like multiplying the whole thing by 1/6. That's the same thing as dividing by 6, right? Then I raised it to the power of a half instead of using the square root. I pulled, because we can distribute this 1/2 to each of the terms inside, right, when they're being multiplied. So I took the power of 1/2 to the 1/6 to just take it outside of the brackets essentially. And then I took the derivative of this part, which ended up being this part right here. 1/2 of what's inside to the power of negative 1/2 times 2x minus 2, which is the derivative of the inside. Notice how I left the plus minus here, because there are essentially two separate derivatives of this, the positive version of it and the negative version of it. If you graph the original function in Desmos, you'll see why. It's actually a shape called a hyperbola that has two separate branches that go along with it. We also, of course, could simplify this thing a lot, but let's leave it like that for now. So this is an okay way of doing this, but it's a bit of a pain to isolate y each time, right? It would be nice if there was a way to just leave y where it was and take the derivative of the thing, right? So there actually is a way to do that, and that's called implicit differentiation, where we leave the y where it is, and we actually use the chain rule to sort of compensate for the fact that y is in there. One thing we have to keep in mind while we're doing this process is that y is the dependent variable. Dependent variable, which means whatever x value is, that's going to determine what the y value is. So you can think of y as being made up of x's, and we can see that right here when we solve for y explicitly. Y is determined by what the x value is, right? So because y is the dependent variable, and we're going to be taking the derivative with respect to x, we need to do something a little bit special with that y. But I'm going to start by actually just copying out that question over here. 6y squared minus 5 equals x squared minus 2x plus 5. when we take the derivative implicitly, so without solving for y, we can actually treat both of the sides of the equation as sort of a separate derivative and take the derivative of the left side and the derivative of the right side. So first of all, what I'm going to do is I'm just going to sort of ignore that y, and I'm going to take the derivative of the right side by itself, because that one's easy. We know how to do that one. The derivative of that is just going to be 2x minus 2, right? The derivative of the left side is a little bit more tricky. Well, we know that negative 5 is just going to disappear, right? Because it's a constant, and the derivative of a constant is always going to be 0. But how do we determine the derivative of 6y squared? So I'm actually sort of going to go off to the side here, or down here, I guess. Let's look a little bit closer at 6y squared. Remember, we're trying to take the derivative of this function in terms of x, right? There is no x here, but remember, y is actually made up of x's, right? Because y is the dependent variable and is dependent on x. So just as a sort of an aside, another example, what if our function was this? 6, x squared minus 5 to the power of 2. So let's pretend just for a second, this isn't true, this isn't what y is, but let's pretend it's true. How would we take the derivative of this function? Well, to take the derivative of that, we can use the chain rule, right? We multiply 2 by 6 to get 12, right? And then we would leave this part the way it is, and then we multiply by the derivative of what's on the inside, which in this case would be 2x, right? So to take the derivative here, what we essentially have is we brought down that 2, we left this thing here inside the brackets by itself, and then we multiplied by the derivative of x squared minus 5. So let's follow the same pattern for this now. Bring down the 2, multiply it by 6, so we get 12. Now the y part, remember, we don't know what y stands for. We know it's going to have a bunch of x's in it, but when we take our derivative, we leave that part by itself. And then what we do is we multiply by the derivative of y. We don't know what y is, so we don't know what the derivative of y is. So why don't we just call that dy by dx, right? Think about it this way. This is exactly the same as this. If y was x to the power of 2 minus 5, right? We'd have the 12y times the derivative of it. Now, can we just use this for the derivative of this? We can. We can actually just plug it directly in there. So we would get 12y dy, I'm going to do times dy by dx. And remember what our goal here with this question. If you look at what our question was actually originally asking for, it was asking for, if we go all the way up to the top, find the derivative in terms of x. So essentially what we're trying to find is dy by dx. Now we have a dy by dx in our equation, right? So if we wanted to find that, we can just isolate for that. So let's do that. If we bring that 12y to the other side, essentially we divide both sides by 12y, right? And divide by, oops, let's not use yellow. Divide by 12y, divide by 12y. Those are going to go away. We're left with dy by dx equals 2x minus 2 over 12y. This is the derivative of our function. Now, you'll notice it's a little bit different than the answer we found to the left, right? We found that the derivative should be this thing, right? Oh, I realized I made a mistake here. I forgot to put y prime here, right? That should be y prime. Anyways, dy by dx. This is actually dy by dx as well, right? dy by dx. So notice how it looks a little bit different. These two things look a little bit different. This is a lot simpler. But the major difference is that this one contains a y, right? Now, we know what y is because we found it over here. If we were to plug in this for y, we would actually end up with this same expression here. You can try it yourself if you want. Plug in y as this value into this, and you'll get the same expression here. So the point is, we were able to find the derivative dy by dx without solving for y. We end up with a y in our derivative, but that's okay. Some of the time we want to just have x's in our derivative, but some of the time it's okay to have a y in there, especially if we're just trying to find the derivative at a specific point on the graph. We can just plug in the x and the y coordinate of that point in order to find the derivative. And clearly this is a lot simpler than this. So just to sort of summarize what the little trick we did here was, we basically were able to take the derivative of the left side and the right side separately. Where we had a y, we had to use the chain rule to come up with this expression in order to find it, and then we had to just isolate for dy by dx because that's what we're looking for. So let's go on to the next question. If you're still a little bit confused about it, it's okay, but let's go on to the next question to see how this looks. Okay, this is an example of a function, actually it's not a function, it's a relation, where we can't really solve for y, we can't isolate for y, so we can't find the explicit derivative. We're stuck with finding the implicit derivative. So we can do that, we have the tools to be able to do that, right? And we're essentially going to take the derivative of the left side and the right side in order to do that. So let's start off with this first term, y to the power of 5. How do we determine the derivative of this? Well, just off to the side, I'm going to do it off to the side again until we get the hang of it. Remember, y is a variable that's in terms of x. So when we're trying to find dy by dx, the derivative in terms of x, we need to take into account the fact that the y contains x's. So the way we find the derivative of this is we use the chain rule, bring down the 5 in front of the y, and then we're going to multiply, or actually that's going to become 5y to the power of 4, but we have to multiply by the derivative of y, which we would just call dy by dx. So that's the thing, this thing here is what takes the place of the y to the power of 5 when we take the derivative. That is the derivative of y to the power of 5. So it's going to be 5y to the 4 times dy by dx plus, we have another y. So we have to use the chain rule once again, right? Now this is y to the power of 1. What's the derivative of a variable to the power of 1? Well, it's just going to be 1, right? So essentially what we have here is 1 times the derivative of y, we have to use the chain rule again, dy by dx. Can we take the derivative of x to the power of 7? Yeah, that one's easy. That's just 7x to the 6. And 2x is just the derivative of that is just 2 equals 0. 0 on the other side, the derivative of 0 is just 0, right? So there we go. We have taken the derivative of this function, or this relation, I should say. But we have two dy's by dx's, and we essentially want to isolate for that to find the actual derivative explicitly. So notice how both those first two terms have dy by dx's in them. So let's factor that out. Dy by dx times what's left, 5y to the 4 plus 1. And then we have over here this plus 7x to the 6 plus 2 equals 0. Well, if we're trying to get dy by dx by itself, we can move that 7x to the 6 plus 2 to the other side, and it's going to become dy by dx times 5y to the 4 plus 1 equals negative 7x to the 6 minus 2. And then in order to isolate that dy by dx, we can just divide both sides by 5y to the 4 plus 1. That's going to cancel out, and we're left with dy by dx is equal to negative 7x to the 6 minus 2 over 5y to the 4 plus 1. There we go. That's our derivative, our explicit derivative. We did the derivative implicitly, but at the end we end up with dy by dx. Notice again how our derivative has x's and y's in it, and that's perfectly fine. So I want you to try example 2 by yourself. It says find the derivative of the following function at the point to 1. And I actually should tell you, find the derivative of the following function in terms of x. We could actually find the derivative in terms of y as well. But when we're talking about the derivative, usually we're looking at how y changes with respect to x, right? We're looking for the slope of a line is usually a rise over run. If we find the derivative of y, we'd be essentially finding the run over the rise, which isn't useful to us at this time. So let's take the derivative of this. I'm actually going to ask you to pause the video here, try this question yourself. When you get stuck or when you're done, you can unpause to see the answer. So here is the derivative that I took of that function. So notice how first I took the derivative of y squared, which is 2y dy by dx using the chain rule. This part is a little bit more complicated. What's the derivative of xy in terms of x? Well, I actually used the product rule here, right? Because we're taking the derivative of two things that are multiplied by each other. This 3x part is easy. The derivative of that is just 3. And the derivative of 9 is just 0. That part's straightforward. But this part here is a little bit complicated. So if you're stuck on that, let's just pull that off to the side. We're essentially trying to find the derivative of x times y, right? If we look at this as like f and g, using our product rule, we know that the derivative of that is going to be f prime g plus fg prime, right? So if we follow that pattern, f prime, the derivative of x is just 1, so it's going to be just y, right? Because it's 1 times y, plus fg prime, f is just x, and g prime is just the derivative of y. The derivative of y in terms of x, we know is just going to be 1 times dy by dx. So essentially this comes out to y plus x dy dx, which is what I put in here, okay? Then what I did is I factored out the dy by dx out of these two terms, and I brought the y plus 3 to the other side and divided to get our answer. Now this actually, the question actually asks us to find the derivative at the point 2, 1. So if we know that point 2, 1 is a point on the graph, we can easily just plug in dy, we can plug in, so at 2, 1, we can just plug in the derivative is just going to be, the y value is 1 plus 3, so 4 over 2 times y, so 2 times 1 plus 2, that's 2 plus 2, 4. So this just equals 1. There we go. So we were able to actually use this derivative even though it has y's and x's in it if we're just trying to find the slope at a point. So there we go. That's using the derivative that we took implicitly.